Hello everyone, I'm Thomas Carrier, and today I'm going to be doing a little overview about steam traps. So I'll start off with a little preview of what we're going to see today. I'm going to start with the definition of a steam trap and then go into the different reasons that we have for them. At the end, I will talk about the different types of steam traps that are commonly used. So the official definition of a steam trap is an automatic valve that is designed to stop the flow of steam so that heat and energy can then be transferred, and the condensate and air can then be discharged. Ultimately, what this means is that it is a piece of equipment that can separate liquid water and air from steam lines. I'll be going into this definition in more details in the coming slides. The first aspect of this definition is the fact that a steam trap is an automatic valve. Steam traps used to be manually operated, however, this obviously took a lot of time and manpower, so automatic valves took over. This does, however, suggest that these valves are controlled by some sort of physical property within the steam line. We'll go into this later in the presentation. The next important aspect of this definition that we want to talk about is the steam and the condensate. So plants use steam for heating process fluids or for driving equipment such as turbines. In fact, 90% of the world's power is made from steam-driven turbines. However, as we've talked about previously in this class, whenever heat energy is lost within steam lines, the steam will condense and turn into liquid condensate. So steam is a valuable asset for plants because it can move machinery and provide heating. However, the condensate is less valuable to them, so we want a way to remove this liquid from the steam. In addition, the condensate can be damaging to things like turbine blades within the machinery. So as I've alluded to, there are two main reasons for steam traps. The first one is to remove liquid condensate. So this lowers the operating costs because the steam can then be reused and heat up other process fluids. It also lowers the maintenance costs though because removing the liquid from the steam lines causes less damage to pieces of equipment such as compressors and turbines. It's also better for the environment just by recycling the liquid and the steam because we then have to use less natural resources and less energy moving forward. The second reason for the steam trap is to vent air. The trap and the pipeline won't work properly for steam applications unless the air is vented in the beginning, but I'll talk a little bit more about this in the coming slides. So the first reason for the steam traps was to remove the liquid condensate. If the liquid is allowed to build up, it can freeze, and as we know, that can burst the pipes. The liquid can also impede the heat transfer of the steam, and it just takes up space that the steam could be taking up. Both of these factors lower the efficiencies of the steam heat transfer. It can also damage equipment, like I talked about previously. It can cause cavitation if the liquid gets through the pipe. However, it can also cause something called water hammer, which I'll talk about more on the next slide. There are many different types of water hammer. However, the one that's relevant here is flow shock. So steam moves about an order of magnitude faster than the liquid condensate within these lines. However, the steam can pick up small amounts of this liquid that sits below it, and then that liquid can start moving at that 65 to 100 feet per second of steam. So this liquid will then keep moving up until it hits some sort of turn, elbow, or other piece of equipment further down the line. And when it hits this piece of equipment, it can either cause an annoying noise, which is where the term water hammer comes from, or it can cause the whole entire pipe to move off of the supports that hold it up. It can even cause the pipe to fracture and burst out into the open. Needless to say, this is not something that we want to happen within our pipe systems, so we want to install some condensate steam traps so that we can prevent this. The next reason for a steam trap was air venting. So before startup, these pipelines that the steam is going into is filled with air. However, this air can impede the flow of the steam. So when we are entering the steam into the pipeline, we need somewhere for that air to go. And the steam traps are often the contraption that is used to vent the existing air within the pipes so that it can then be filled with the steam. So now that we know a little bit about what a steam trap does, we can look at the different types of steam traps commonly found in plants. There are three different kinds: mechanical, thermostatic, and thermodynamic. Mechanical traps are controlled by density, thermostatic traps are controlled by temperature, and thermodynamic traps are controlled by the velocity. The first trap we're going to talk about is a mechanical trap, and it is the float and thermostatic trap. That's two words, but it's one type of trap. This trap is density controlled because that ball you see on the right side will float up and down dependent upon the level of liquid within the trap. The ball is then attached to a lever which controls a valve that either opens or closes depending upon the height of the ball. The thermostatic air vent is that yellow and red thing that you see on the top right of the trap, and this vent opens at a temperature slightly below the saturation temperature of water, which means that a little bit cooler air can flow through the vent and exit the valve, but the steam cannot flow through and is instead hindered. The most common application for this trap is the process line, although it's also widely used in other applications. So the second type of trap that we're going to talk about is the inverted bucket mechanical trap. This is a density controlled because there is an upside down bucket within this trap that when filled with a liquid condensate alone will sink to the bottom and the trap will remain open. However, when 2/3 of this bucket is filled with steam, the trap will float up and it will close the valve at the top until the steam loses enough heat energy and condenses back into the liquid, and the bucket will then sink again. There is a hole in the top of the bucket that allows the air to flow through it and collect in the top chamber, which will then be released whenever the valve is open next. The most common application for this is steam distribution lines. The first type of thermostatic trap that we're going to talk about is the liquid expansion trap. As we know, thermostatic traps are temperature controlled. This trap is temperature controlled because there is an oil cylinder, which is the orange and brown stuff you see in the picture, which expands when the temperatures get higher and contracts when lower. So whenever the temperatures are high, the trap will expand and the valve will be seated on the seat that you see there and close. So at normal temperatures, air and everything is freely flowing throughout this trap. However, whenever it gets hot, it closes and everything stops. So this can result in the buildup of some liquid within the trap, so it has to withstand some water logging. It's beneficial though because it controls the exit temperature, which means that the common application for this is a hot water tank. The second type of thermostatic trap is the balanced pressure trap. So as we know, this trap is temperature controlled, and it's temperature controlled because that yellow and orange liquid that you see in the figure is actually a mixture of alcohol and water, which vaporizes at a temperature lower than water. So this means that when hot steam enters and flows through the steam trap, it'll expand that mixture within the capsule, which then pushes the valve closed. So, like in the previous trap, whenever this trap is open, air will freely be flowing through it. However, if it's closed, it stops the flow of everything, which means that it also has to withstand water logging. The most common application for this is during startups, because the air is freely flowing through, so the air can be exiting during the entire startup process. However, it is usually used in parallel with another type of trap. The final type of thermostatic trap is the bimetallic trap. So as we know from materials class, different materials expand at different rates when heated up. So whenever two dissimilar metals are welded together, they will expand at different rates and deform. So when we attach these two different types of metals and then heat them up with steam or condensate, they will expand. And the way this trap works is that it pulls up on the lever, which then seals and closes the valve. So like the other two traps, air freely flows when this is open. However, this trap often closes early because it often activates at a temperature below the saturation temperature of water, which means that there's often gas left within the trap. This also means that water logging occurs within this trap as well. The benefit of this trap is that it can withstand heavy water hammer though, and its main use is in a drip station. The final trap we're going to talk about is the thermodynamic trap, which as we know is velocity controlled. Contrary to its name, this trap is actually known to be the most simply operated trap. So how it works is that whenever liquid is flowing through it, it lifts the disk to the top and freely flows. However, whenever steam enters the trap, it expands rapidly in the bottom chamber, which causes a flash of a high velocity to shoot up to the top and hit the disk. And as we know due to Bernoulli's principle, whenever there's a higher velocity, the pressure drops. So therefore, the now higher pressure at the top chamber pushes down on the disk and closes it. This will remain closed until the higher pressure steam in the top chamber condenses, and then the process starts over again. This one negative effect of this trap is that air during startup can move too fast and close the trap, which is not what we want. However, this trap can withstand heavy water hammer, so it's often used for steam distribution and steam tracing lines.